Welcome! In this session, we will explore LeetCode problem number 572, titled Subtree of Another Tree. This is a fascinating problem that challenges us to determine whether one tree is a subtree of another. We'll cover intuitive approaches, analyze their complexities, and provide clear explanations to help you master this concept. Let's dive in. In this problem, we are given the roots of two binary trees, root and subroot. Our goal is to determine whether subroot exists as a subtree within the larger binary tree root. Here, a subtree is defined as any node in the tree along with all of its descendants. It's important to note that the entire tree itself can also be considered a subtree. For the input, we are provided with the root node of both the main binary tree, root, and the smaller tree, subroot. The output is simply a Boolean value, where true means subroot is a subtree of root, and false means it is not. This makes the problem straightforward to state, but implementing it efficiently requires careful consideration. Now, let's look at an example to understand this better. Suppose the main tree, root, is represented as 3, 4, 5, 1, 2, and the smaller tree, subroot, is 4, 1, 2. The goal is to check whether subroot exists as a subtree in root. First, let's visualize the structure of the root tree. It has 3 as the root node, with 4 as its left child and 5 as its right child. The left subtree of 4 contains nodes 1 and 2 as its children. So, the tree structure of root is clearly defined, and we can now evaluate if subroot fits as a subtree within it. The structure of subroot is simpler. It has 4 as its root, with 1 as the left child and 2 as the right child. When we compare this to the left subtree of root, we can see that it matches exactly. The node values and their arrangement in subroot align perfectly with the subtree starting at node 4 in root. Since the structure and values are identical, we can conclude that subroot is indeed a subtree of root. Therefore, in this case, the output is true. Let's consider another example where the root and subroot trees are similar but have slight differences. Here, the root tree is 3, 4, 5, 1, 2, null, null, 0, and the smaller subroot tree remains 4, 1, 2. If we visualize root, it's clear that node 4 has the same left and right children, 1 and 2, as in the previous example, but now the left child 1 also has an additional child, node 0. This extra child makes the subtree starting at 4 in root structurally different from subroot. As a result, even though the values of some nodes match, root contains extra nodes that are not part of subroot. Therefore, the output for this example is false. Now, let's discuss the constraints and some edge cases to keep in mind. The number of nodes in root can range from 1 to 2000, and subroot can have up to 1000 nodes. Additionally, the node values can range from -10⁻4 to 10⁻4, so we must account for negative values during comparisons. An important edge case is when root and subroot are identical. In such cases, subroot is automatically a subtree of root. Another case is when subroot consists of a single node, and we need to check if any single node in root matches it. Finally, if subroot has more nodes than root, it's impossible for it to be a subtree, and the result should be false. These constraints and edge cases help define the problem clearly and guide us in creating robust solutions. To begin understanding the problem, we can consider the brute force approach. The idea here is straightforward. For every node in the main tree, which we call root, we check if the subtree starting at that node matches the given subroot. This is achieved using recursion. The helper function is key. It ensures that the two trees being compared are structurally identical and that their values match at every corresponding node. While this approach is intuitive and easy to implement, it has significant inefficiencies. Specifically, the time complexity is O, n asterisk m, where n is the number of nodes in root and m is the number of nodes in subroot. This occurs because for every node in root, we may end up comparing all the nodes in subroot. Additionally, the space complexity is determined by the recursion stack, which depends on the height of both trees. While simple, this approach can be impractical for large trees due to the redundant comparisons it performs at every step. An optimized alternative to the brute force method is to use a serialization approach combined with string matching. The intuition here is to represent both trees as serialized strings using pre-order traversal, including markers for null nodes to preserve their structural integrity. Once serialized, we can use efficient string matching techniques to check if the string representing subroot is a substring of the string representing root. This reduces the problem to a substring search, which can be performed in linear time using algorithms like KMP or simply Python's in operator. The time complexity of this approach is O, n plus m, where n and m are the number of nodes in root and subroot, respectively, and the space complexity is also O, n plus m, for storing the serialized strings. However, this method comes with trade-offs. While it avoids the repeated recursive comparisons of the brute force approach, it introduces extra memory overhead for storing the serialized strings. Additionally, there is a risk of edge cases where different trees may produce similar serialized strings, leading to potential misidentifications. Another optimized strategy is a recursive approach that combines tree traversal with subtree matching. The main idea is to traverse the main tree root using depth-first search and, at each node, check if the subtree rooted at that node matches subroot. This is achieved through a helper function that recursively compares the two trees, ensuring that both their structures and their node values are identical. The process involves two main steps: first, traverse root node by node, and second, for each node, invoke the helper function to check for equivalence with subroot. While the worst-case time complexity remains O, n asterisk m, similar to the brute force approach, the practical performance is often better due to early termination when mismatches are detected. The space complexity is reduced to O, h, where h is the height of root, as it only requires the recursion stack for traversal. This approach avoids the additional memory overhead of serialization and keeps the implementation more intuitive, though it may still perform redundant checks in some scenarios. After evaluating the various approaches, the recursive traversal with subtree matching emerges as the most balanced solution. It offers simplicity in implementation while maintaining reasonable efficiency in both time and space. Serialization, while faster in certain cases, introduces additional memory overhead and potential risks with string representation collisions, making it less robust. The brute force approach, on the other hand, is straightforward but highly inefficient for larger trees due to its redundant computations. The key insight in the recursive traversal approach is the ability to short-circuit mismatches early, which avoids unnecessary comparisons. This makes the solution cleaner and easier to debug while still being efficient enough for most practical scenarios. Although it may still perform redundant checks in the worst case, it avoids the pitfalls of string-based methods and provides a clear, well-structured approach to solving the problem. To solve the problem of determining if one tree is a subtree of another, we begin by understanding the conditions that make this true. For a tree's subroot to be a subtree of root, there must exist a node in root where the subtree rooted at that node is identical to subroot. Identical means that both the structure of the trees and the values at each corresponding node match completely. With this in mind, a high-level approach involves traversing the root tree and, at each node, checking if the subtree rooted there matches subroot. To implement this, we use a recursive brute force algorithm. We start by traversing the root tree recursively, examining each node's left and right subtrees. At each step, we'll use a helper function to check if the subtree rooted at the current node is identical to subroot. This forms the foundation of our solution. The core of the algorithm lies in two main parts: tree comparison and subtree verification. For tree comparison, we begin by checking if the current node of root matches the root of subroot. If their values align, we then recursively compare the left and right children of both trees. If all corresponding subtrees match, we return true, indicating that the two trees are identical. Otherwise, we return false. After performing this check, we make the final decision. If any node in root passes the subtree check, then subroot is indeed a subtree of root, and we return true. If no such node exists, we return false. To clarify this further, we can look at the pseudocode for the is_same helper function. This function checks if two trees are identical by comparing their root values and recursively ensuring their left and right subtrees match. Similarly, the is_subtree function navigates the root tree and uses is_same to verify if subroot matches at each step. Notice how the base cases handle scenarios where either tree is null, ensuring the algorithm doesn't fail in edge cases. In the pseudocode, the decision-making process becomes clearer. If the is_same function confirms that the current node of root matches subroot, we immediately return true. If not, we proceed to recursively check the left and right subtrees of root for potential matches. This ensures that every node in root is considered as a possible starting point for subroot. The recursive nature of this solution is key. The helper function is_same provides precise subtree matching, ensuring that both the structure and values are verified. Meanwhile, the main function is_subtree guarantees a thorough traversal of the root tree, exploring all potential nodes where subroot could match. Additionally, the base cases handle edge conditions, such as when root is null, in which case there's no subtree to check, or when subroot is null, which makes it trivially a subtree of root. These insights solidify the correctness and completeness of the algorithm. The algorithm relies on two main data structures to function effectively. First, the tree nodes themselves, which contain a value and references to their left and right children. This structure allows for efficient traversal and comparison during the subtree checks. Second, the recursion stack, which is used implicitly during the traversal. As the algorithm explores deeper levels of the tree, the stack keeps track of the recursive calls, and its depth corresponds to the height of the tree. Now, considering the complexity analysis, the time complexity is determined by the number of nodes in root and subroot. For each node in root, the is_same function compares up to m nodes in subroot. In the worst-case scenario, this leads to an overall time complexity of n*m, where n is the number of nodes in root and m is the number of nodes in subroot. The space complexity is dictated by the recursion stack, which, in the worst case, has a depth equal to the height of the tree. This results in a space complexity of h, where h is the height of root. These analyses give us a clear understanding of the algorithm's efficiency. Finally, let's consider the edge cases to ensure the algorithm handles all possible scenarios. If subroot is empty, it's always considered a subtree of root, so we return true. Conversely, if root is empty, it cannot contain any subtrees, and we return false. Another critical case is when subroot is larger than root. Since it's impossible for a larger tree to be a subtree of a smaller one, we return false. Lastly, if root and subroot have the same structure but different values, the algorithm ensures that value comparison prevents false positives, thereby maintaining accuracy. These edge cases highlight the robustness of the solution, covering all possible inputs effectively. This code solves LeetCode problem number 572, subtree of another tree. The problem requires us to determine if the tree subroot is a subtree of the tree root. A subtree means that some node in root has an identical structure and values as subroot. First, we define a helper function r_identical, tree1, tree2, to determine if two trees are structurally and value-wise identical. This function checks 1. If both trees are none, they are identical. 2. If one tree is none and the other is not, they are not identical. 3. If both trees are not none, it recursively checks if their root values are equal and if their left and right subtrees are identical. Next, in the main function is_subtree, root, subroot, we handle the base case where root is none. If root is none, it cannot contain any subtree, so we return false. Otherwise, we check if the trees rooted at root and subroot are identical using the r_identical helper. If they are, we return true. If they are not identical, we recursively check if subroot is a subtree of the left or right subtree of root. This is done by calling self.isSubtree, root.left, subroot, and self.isSubtree, root.right, subroot. This approach ensures that we traverse the entire root tree and compare each subtree with subroot. The recursion stops when either an identical subtree is found or we've traversed the entire root tree. This solution is efficient and concise, leveraging recursion to perform subtree checks without unnecessary computations. It handles all edge cases, including when root or subroot is empty or when subroot is larger than root. Here, we start by defining the isSubtree method, which determines if the tree subroot is a subtree of root. The first condition checks if root is null. If it is, then subroot cannot be a subtree, so we return false. Next, we check if the two trees are identical using the r_identical helper method. If they are, we return true. If not, we recursively call isSubtree on the left and right subtrees of root, combining the results with a logical OR. This ensures that we explore all possible subtree positions within root. Then, we define the r_identical method, which checks if two trees are structurally identical. The first condition checks if both trees are null. If they are, they're considered identical, so we return true. However, if only one of the trees is null, they cannot be identical, and we return false. Now, within the are_identical method, we verify if the values of the current nodes in tree 1 and tree 2 are the same. If they match, we recursively compare their left and right subtrees. For the trees to be identical, all these conditions must hold true, the values of the nodes must match, and both the left and right subtrees must also be identical. Finally, we define the treenode class, which represents the structure of a tree node. Each node contains an integer value val and references to its left and right child nodes. This class is fundamental for constructing binary trees and is used throughout the implementation to represent the nodes of root and subroot. In this first example, we are given a root tree with values 3, 4, 5, 1, 2, and a subroot tree with values 4, 1, 2. We start by checking the root of the root tree, which has a value of 3, and compare it to the root of the subroot, which has a value of 4. Since these values do not match, we proceed to check the left and right subtrees of the root. Next, we move to the left child of the root, which has a value of 4. This time, the values match, so we need to verify if the two trees rooted at these nodes are identical. To do this, we call the helper function are_identical on tree 1, the subtree starting at root.left, and tree 2, the subroot. The root values of both trees are 4, so we then compare their left and right subtrees. First, we compare the left children, which both have values of 1. When we compare the left children, both nodes have a value of 1. Additionally, both their left and right children are none, so this part of the trees is identical. Moving to the right children, we compare the nodes with values 2 in both trees. Again, the values match, and both their left and right children are none, confirming that this part of the trees is also identical. Since both the left and right subtrees of tree 1 and tree 2 are identical, we conclude that the two trees rooted at these nodes are identical, and the function returns true for this subtree check. Therefore, the output for this example is true, indicating that subroot is indeed a subtree of root. In the next example, we will examine a case where the subtree does not exist in the root tree. Here, the root tree is 3, 4, 5, 1, 2, null, null, 0, and the subroot tree is 4, 1, 2. Starting at the root of the root tree, which has a value of 3, we compare it to the root of subroot, which has a value of 4. These values do not match, so we check the left and right subtrees of the root. Moving to the left child of root, which has a value of 4, we see that it matches the root of subroot. We then call the are_identical function to check if the trees rooted at these nodes are identical. The root values are identical, so we proceed to compare their left subtrees. Both left children have a value of 1, which matches. However, when checking the left and right children of this node, we find that the left child of tree 1.left has a value of 0, while tree 2.left has no left child, none. This mismatch means the trees are not identical at this node, and we return false. Since the subtree check failed at root.left, we move to root.right, which has a value of 5. Comparing this value to the root of subroot, which is 4, shows they do not match. As no subtree of root matches subroot, the output for this example is false. In the final example, the root tree is 1 and the subroot tree is none. Here, we follow the rule that if subroot is none, it is always considered a subtree of any root tree. This is because a none tree can trivially fit anywhere within another tree. Therefore, we immediately return true for this case. The final output for this example is true. To analyze the time complexity of our solution, we focus on the two primary functions, isSubtree and are_identical. Starting with are_identical, this function is responsible for comparing two binary trees node by node. In the worst-case scenario, it needs to check every node of both trees, making a recursive call for each node. If the first tree has m nodes and the second tree has n nodes, the time complexity of are_identical is O min ism n, because it only compares nodes up to the size of the smaller tree. Now, looking at the isSubtree function, it traverses the entire root tree, analyzing each node to determine if it could serve as the starting point for subroot. For every node in root, it calls are_identical to compare the subtree starting at that node with subroot. If the root tree has n nodes and the subroot tree has m nodes, the worst-case time complexity arises when every node in root triggers a full check via are_identical, resulting in an overall complexity of n*m. Now, considering the best-case scenario, the first node of root matches subroot, and are identical quickly confirms their equivalence. This would take only m time, as it avoids additional comparisons. For the average case, the algorithm may traverse part of root and compare subtrees for a subset of nodes. While it is challenging to precisely quantify the average case, especially for arbitrary binary trees, the time complexity tends to approach the worst-case complexity of n*m for large or unbalanced trees. Shifting to space complexity, we begin with the recursive call stack for are identical. The depth of recursion is determined by the height of the smaller tree being compared, which, in the worst case of completely skewed trees, is m. Similarly, for is subtree, the recursion depth depends on the height of the root tree. If root is also completely skewed, the space required for its recursion stack is n. When combining these two components, the total space complexity becomes n plus m, as the recursive calls for are identical and is subtree occur independently. Let's compare this approach to a naive alternative, where all possible subtrees of root would be generated and checked against subroot. This naive method introduces a massive overhead, as generating all subtrees of root takes exponential time, making it highly inefficient. In contrast, our optimized solution avoids this overhead by directly checking each node of root recursively, achieving a significantly better time complexity of n*m. To summarize, the optimized approach provides a time complexity of n*m and a space complexity of n plus m, making it far more practical and efficient than the naive alternative for solving this problem. When working on this problem, there are some common mistakes to be aware of. First, not handling null cases properly can be a major pitfall. If either the root or subroot is null, you need to account for these edge cases. For instance, if root is null but subroot isn't, the answer should be false. Skipping these checks can lead to runtime errors. Next, inefficient comparison logic can hurt performance. If your recursion structure repeatedly compares the same subtrees, you're wasting valuable computation time. Using helper functions effectively can eliminate redundant calculations. Another mistake involves confusing the matching logic itself. It's easy to mix up the base case for functions like isSameTree with the logic for traversing the tree. Make sure your base cases are clear and distinct. Additionally, underestimating the time complexity is another error to avoid. Remember, in the worst case, the time complexity for comparing two trees is n*m, not n plus m, so plan accordingly. Finally, don't overlook edge cases involving single-node trees. Testing with minimal and maximal input sizes is crucial to ensure your solution is robust. Now, let's focus on insights that are particularly useful in interview settings. This problem is a great example of pattern recognition. It's a variation of tree traversal and subtree matching problems, so familiarity with patterns like DFS and BFS will give you an edge. Optimization is another key focus during interviews. Many candidates stop at brute force solutions, but you can stand out by discussing techniques like pruning unnecessary recursion, such as terminating early when node values don't match. It's also important to clarify assumptions up front. For example, ask whether duplicate values are allowed in the tree, as this can significantly affect how you verify matches. Demonstrating clean coding is equally important, and one way to do this is by writing modular code. Breaking the problem down into smaller functions, like isSameTree, not only makes your code more testable but also shows that you're organized in your approach. Additionally, similar problems can help deepen your understanding. Examples include Problem 100, which asks you to check if two trees are identical, and Problem 617, which involves merging two binary trees. Both build on similar concepts of tree traversal and manipulation, making them excellent practice. There are also alternative approaches to solving this problem, each with its own trade-offs. The brute force approach, which involves comparing nodes one by one, is straightforward and simple to implement. However, it's highly inefficient for large trees, with a time complexity of n*m. While it might work fine for small inputs, it's not ideal for more complex cases. A more optimized method involves using DFS with early termination. This approach prunes unnecessary recursion by stopping comparisons as soon as a mismatch is detected. It's faster for larger inputs but does require slightly more complex logic. For those looking for a more advanced solution, tree hashing is an interesting option. By pre-computing hashes for subtrees, you can significantly reduce comparison time to O(n plus m). That said, this method is harder to implement and debug, which might make it less practical in an interview setting unless you're highly confident with the technique. Each of these approaches has its strengths and weaknesses, so it's important to choose the one that best fits the given constraints and scenario. Great job! To summarize, we explored how to determine if one tree is a subtree of another, discussed the brute force approach, and analyzed its complexities. Remember to practice tree traversal techniques and recursive problem solving. Thank you for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!